Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another interesting topic and of my presentation series. And this time, the presentation topic is components of a substation and electrical layout of a substation. My good name is John Kweku Amu-Otu, and I've been an electrical engineer, professional electrical engineer for the past 31 years. And I am based in the United States of America. If you watch my presentation and you like my presentation, don't hesitate to click the select button, which is basically the like button in YouTube, and also go ahead and share this presentation, and also select the subscribe button as shown over here. Now let's pivot on to the outline of my presentation. The first item of my presentation is I'll go through the definition of a substation and its function. Basically what delineates what a substation is and the various functions that a substation layout performs. Then we'll look into the flow line that basically shows all the processes that are associated, from generation, transmission, sub-transmission to distribution to the load end of the consumer. Then we'll talk about the types of substations that we have out there. And basically the types of substation we have is generation substation or switchyard. Usually some people call it a switchyard and some people call it a substation because it is very close to the generation source. So that is why some people call it a switchyard instead of a substation. Then we'll talk about transmission level substation, then sub-transmission level substation, then distribution level substation. Then the last but not least, we'll talk about the various components and the various equipment that are located in a substation environment. Now, let's talk about what is a substation and its functions that it's supposed to perform. It is utilized in the generation, sub-transmission, distribution, power system network. So as you can see, a substation basically integrates in between these flow lines. It is, it starts from the generation end, and basically, is from the generation you have a substation or a switchyard that is integrated in between the generation and transmission level. Then from the transmission level, you have a substation that basically transmits is integrated to the sub-transmission level. Then from the sub-transmission level, you have another substation that integrates into the distribution level before it gets to the customer. It is utilized in a generation network, So let's talk about all the generation power sources that we have. The first one we have is the wind power generation, right? Okay, so if you have a wind power generation, basically that consists of many wind farms that are arranged in various configurations. Then connected here will be, let's take an example for an onshore wind farm, right? Okay, so right here will be a substation, right? That is supposed to harvest all the wind power that is generated by these many wind farms, right? Okay, so there is a substation here that steps the voltage up from, let's say, collection voltage of, let's say, 333 kV to, let's say, 230 kV, or 66 kV to 230 kV. Next energy power generation energy source that is integrated to a substation is a nuclear generation power plant, right? Okay, so if you have a nuclear generation power plant, right, and inside the nuclear generation plant, you have a generator, a big generator. Let's say you have a 650 MVA generator, right, with an output voltage of 18 kV. And sometimes you can have like, let's say 20.2 kV as the output voltage, right? Okay, so this is integrated to a generator step-up transformer, right? That steps the voltage from 80 kV or 20.2 kV to, let's say, 230 kV or 345 kV, right? And this is achieved in a switchgear, right? So that is what I made mention that that is the first type of substation we have. And most often than not, some people utilize the wording of generation substation instead of a switchgear, but in actual sense, it is a switchgear. Next is a cogeneration source, right? Okay, so this generation power facility basically generates power utilizing coal that is basically pulverized and burned in a boiler, right? Okay, so you have a boiler that basically has a fire inside, and basically it burns and the pulverized coal, right? Okay, on the walls of the boiler, basically you have water that are flowing throughout all the walls of the boiler. And the water that is flowing is achieved by a boiler feed pump motor, right? This basically pushes, and feeds the boiler with that amount of water. And that water is heated by the boiler, right? Basically, combustion the coal powder. And basically, the water basically gains the heat from the boiler, right? And basically, it's a mixture of steam and water. And basically, as it rises up and goes through different reheat sections, and it gets reheated, right? After reheating, basically, you obtain a very dry steam, which is about 96% dry and about 4% moisture, right? So this is fed into a steam turbine generator, and the steam turbine generator basically produces electric power. So the output of the steam turbine generator is 18 kV or 20.2 kV. Then it goes through a switchyard substation that basically there's a transformer there, generator step-up transformer that steps the voltage from 18 kV or 20.2 kV to 230 kV or 345 kV transmission level voltage. Next is geothermal, right? Okay, so geothermal power energy source actually comes from heating underneath the earth, all right? Okay, so if you have the earth's surface, right, and feasibility studies has to be done to identify a location where there is enough latent heat, embedded heat underneath the earth's surface, right? Okay, so typical areas like California, the Middle East, those are areas that there's a lot of heat that is embedded underneath the soil. So that is an area that you can locate a geothermal power plant, right? Okay, so what the geothermal power plant is doing is it is basically leveraging on the amount of heat that is beneath the earth's surface, right? So that amount of heat basically heats a boiler, just like you have for a coal generation source or nuclear generation source, right? You have heat that for a nuclear generation source, you have heat that is created from the nuclear fission process, right? And that heating is transferred to the water, the cooling water that is flowing through the reactor, right? Similarly, for a coal generation source, you have a heat that is created from the burning of the coal, pulverized coal, and you have a feed water heater that gains the heat from the burnt coal and basically turns into steam. So same thing applies to the geothermal energy source, right? you have a energy latent energy source that is embedded underneath the soil, and this heats a boiler, right? And basically, steam is generated, right? And it goes through different cycles of basically improving the efficiency of the power generation cycle. So it goes through a reheat cycle just to make the steam as dry as much as possible before it gets to the steam turbine. Before basically the steam gets impinged on the turbine blades and it rotates the turbine blades, and the turbine blades are connected or integrated to the generator rotor. So as the turbine rotor, the turbine shaft rotates, since it is coupled to the generator rotor, basically automatically the generator rotor starts rotating, and basically magnetic field is created on the generator rotor from an extension system, and the revolving magnetic field basically impinges on the stator, and basically that's how voltage is generated at the terminal, right? So at the switchyard of this geothermal power plant, right? Similarly, you have an output, right, from the generator, and it goes through a generator step-up transformer that steps the voltage from 80 kV to 230 kV or 345 kV transmission level voltage. Next is ocean power energy, right? Okay, so it is basically harvesting energy from the ocean. As you know, those are huge ocean waves. Some of them can be as tall as a skyscraper. Yeah, if you go to deep out there, in areas where you have a lot of, ocean waves. That's how some. So there's a lot of enormous amount of energy that is in this ocean waves. So these turbines that is integrated to a generator is basically located underneath these in these areas that have high and waves to harvest the energy from the waves. So similarly, you have a ocean turbine, right? Okay, that is coupled to a generator, right? So once the ocean wave, or the ocean tidal wave hits the turbine, basically it rotates, and that rotates a generator, and an output voltage is generated. Then it goes through a generator step-up transformer to step up the voltage for transmission level. The reason why the voltage is stepped up for transmission level is because of efficiency and also lower costs. Because as you step the voltage higher, right, you require smaller sections of conductors, and that itself results in lower cost of transmission of power, lower losses as well. Next is a hydro generation, right? Okay, so for hydro generation, right, it utilizes the potential energy, right, from a dam, right? You have basically water that has been dammed here, right? Then you have a penstock, right, piping that is basically integrated to the dammed water that is behind this concrete embankment, right? Okay, so the water goes through the penstock, right? Then you have this vertical turbines, right? That is integrated to a vertical mounted generator. So if the generator is right here, then the turbine is right here, right? Okay, so this type of turbine generator combination that is integrated through a shaft basically rotates at a slower speed, right? So it utilizes a different type of generator called salient pole generator, right? Okay, so it has a lot of poles on the rotor, so the speed is much smaller. So the water that flows through the penstock from this dam over here flows at a very fast energy, and basically there's a lot of potential energy from this height. So as the water impinges on the vertical mounted turbine blades, it rotates it, right? It starts rotating it, and basically rotation starts. And once, because the turbine is coupled through a coupling to the shaft of the generator, or the rotor automatically starts rotating. And basically you have an extension system, right? That basically feeds the rotor winding to basically create a magnetic field, right? Okay, so as the magnetic field of the rotor rotates, basically it cuts the stator. There's a stator winding that is stationary, right? And basically it induces voltage into the stator coils. And so that is how you get voltage out at the output of the hydro generator. Then let's say if the output voltage is 13 kV, right? Then it goes through a GSU, generator step-up transformer, similarly to the other sources of power generation, and it steps the voltage up to either 115 kV or 230 kV or 345 kV transmission level voltage. Next, other source of power energy source is solar PV, right? Okay, so what it's doing is basically it is harvesting and generating electrical power, from the solar energy, right? So you have a lot of solar cells that are connected in an array format, right? In series, in different radio array format, right? So what it does is basically, it harvests the solar energy, and basically it is stored as a DC voltage. Then it goes through a DC to DC converter, right? That steps the voltage up, right, to a higher voltage. Then it goes through an inverter that basically inverts the DC voltage to an AC voltage before it goes to a collection voltage, right? So from the collection voltage, then it goes through a generator step-up transformer that steps the voltage up. Next is a biomass, right? Okay, so biomass. What it's doing is basically, you have trash. A typical example of biomass is renewables, is trash, right? Wood, and basically all this is pulverized. It is crushed into smaller fragments, and basically it is fed inside a boiler. And what the boiler does is basically it boils those trash element, and basically the tree that has been broken down into several pieces. Then from there water is fed through the walls of the boiler, and basically the water basically gains energy, heat from the boiler, and basically converts it into steam. And as the steam basically rises up to the higher section of the boiler, it gets reheated. Because the goal is basically to get the steam as dry as much as possible before it is fed into a steam turbine generator, right? So the steam from the boiler, which is about quite close to 100% dry, let's say about 96%, with a little bit about 4% moisture in it. You have a turbine, right, that has turbine blades. So the turbine has is basically in different sections, right? You have different sections of the turbine. You have the high pressure sections, you have the intermediate pressure section, you have the low pressure sections, right? Okay, so these are various sections of the steam turbine, and it has a shaft that basically integrates all these sections together, right? Okay, so you have a piping that carries the high pressure steam from the boiler, right? Okay, this steam is as dry as much as possible, about 96%, and it flows in the piping at a mass flow rate, right? Okay, so it comes in here, then it hits the high pressure section has a turbine blades, right? And these turbine blades, the high pressure section's turbine blades are very small in dimensions, right? So it hits it, and basically it starts rotating, right? Okay. So that's how it gains that amount of energy from the steam. Right? Basically, it converts that kinetic energy to mechanical energy, right? Ke to mechanical energy. Then, as the steam flows past the steam turbine blades in the high pressure section, right? It basically comes back and goes through the reheat section of the boiler. The goal of the reheat section is to heat it more to make the steam as dry as much as possible. Then it comes back into the intermediate section of the steam turbine. Okay, so the intermediate section, the blades are a little bit larger than the high pressure section, right? So similarly, it gets impinged on the blades and it starts basically rotating, right? To basically convert from kinetic energy to mechanical energy. Then from there, it goes back to the low pressure section, right? Then it impinges on the blades of the low pressure section. So the low pressure section, the blades are much larger than the high pressure section. So as you move or traverse from the high pressure section to the intermediate pressure section of the turbine to the low pressure section, the blades of the turbine gets bigger. So finally, as the steam leaves the low pressure section of the steam turbine, it goes into a condenser, right? So on the walls of the condenser is cold water that is fed into the walls of the condenser. So as the steam basically gets here, then basically it has a higher, let's say, I would say about 60% dry and 40% moisture in it. So as it impinges on the wall of the condenser, it converts into water. Then it goes through a feed water system, feed water pump, right? There's a drain water pump, basically that feeds and pumps the water to the boiler to repeat the cycle. So that's how basically you obtain the cycle, the complete cycle of our power generation, right? From here, it goes to a boiler feed pump, right? From the feed water heater pump, then from here it goes to the boiler. So that's how the cycle repeats. Next is natural gas, right? You are basically generating power from a natural gas turbine, right? So we have combustion turbines out there that utilizes natural gas. So basically, similarly, you have natural gas that is basically it goes through combustion, right? Okay, you have heaters that basically lights just like in your car, you have fuel that flows through your engine, and it gets heated, right? Okay, so basically it creates a fireball, right? So the fireball basically rotates the energy from that basically rotates the turbine, right? That turbine is connected to a generator, right? And turns because they are coupled through a shaft. The generator turns and basically generates a voltage. So the output voltage, let's say 30 kV, then it goes through a generator step-up transformer to step up the voltage to transmission level. Okay, so the next function of a substation is basically it either steps up, right? And I gave you an example of a step-up condition, right? That is right at the switchyard. That is in close proximity to the generation power plant, right? It steps the voltage up from 18 kV to 115 kV, from 18 kV to 230 kV, 18 kV to 345 kV, or 18 kV to 230 kV, right? Or from 20.2 kV to all those higher transmission level voltages. On the other hand, it can also step down, right? In between, let's say you have a transmission level voltage of 230 kV, right? 115 kV, 345 kV, right? And basically, it gets transmitted for, let's say, 100 kilometers, right? There is a substation right here where you achieve a step down. So this substation will, let's say, step it down from, let's say, to 30 kV or 345 kV to, let's say, 115 kV, or 345 kV to 69 kV, right? So that is when a substation steps down the voltage. On the distribution end too, you can achieve a step down condition of a substation, right? Okay, so on the distribution end, you can have a 69 kV transmission level, right? That comes in, that steps the voltage down to, let's say, 12 kV, 13.8 kV, or 4.16 kV. Right? So that is at the distribution level. At the distribution level, you can also have a substation that can step down from 4.16 kV to 480 volts level voltage. So that is the second function of a substation. The third function of a substation is performing a switching function, right? Okay, so as you know, within a substation environment, you have a lot of circuit breakers, right? So we utilize the circuit breakers to basically turn on or turn off the circuit or feed the circuit, right? Okay, and also we utilize the circuit breakers to interrupt. Let's say if you have a fault, we utilize the circuit breaker to interrupt a fault. So that is one of the functions of the switching functions of a substation. The second switching function is after de-energizing the circuit breaker, right? Okay, we have disconnect switches, right? That is a no-load disconnect switches that has to be opened on the no-load conditions to isolate the equipment so that the equipment can be worked on. The next function of a substation is basically it is mostly owned by transmission company and generation company, distribution company, and some industrial companies that also have their own substation. Right? Okay. So substations are mostly digitized, right? Okay, and have control in place, and some of the control have local means of controlling the substation, right? Okay. And it also has a remote monitoring that can be achieved. And for remote monitoring, it has to go through an RTU, right? And that is a remote terminal unit. And basically from the remote terminal unit, it is integrated to a SCADA system. And sometimes also for an industrial facility, you can have a distributed control system, DCS system, that basically is utilized to perform remote control and monitoring of a substation. Now, let's walk through a flow line or a schematic that shows you all the processes that are associated with power generation through transmission level, sub-transmission level, to distribution level, all the way to the customer, the load end, right? Okay, so we have a power station that is here, right? And I went through all the different types of power stations that and the different power generation sources that we can have, right? And let me go refresh your memory on that. We have hydro, right? You can have a hydro power plant, right? We can have a power plant from a coal generation source, right? We can have a power plant for a biomass, right? We can have a power plant from natural gas burning, right? We can have a power plant from wind, right? We can have a power plant from solar, right? We can have a power plant from geothermal, right? And I explained all these sources of power generation sources and how the power generation is achieved and all the processes that are associated with that, right? Okay, so the output of this is a generator, basically generating an output voltage, right? And I indicated that the output voltage could be 13.8 kV, right? It could be 18 kV. It could be 20.2 kV, right? That comes from the generator that is in this power station, right? Okay. So here is where they call it your switch yard, right? And I indicated that some people call it a substation, some people call it a switch yard, but the correct name is a switch yard because that is where a lot of the switching action is taken for you to achieve that transmission level voltage, right? Okay, so you step the voltage up from 13.8 kV, 18 kV, or 20.2 kV to a transmission level voltage of 138 kV, 230 kV, 345 kV, 500 kV, 765 kV. And matter of fact, you can go all the way to ultra high voltage transmission, 1100 kV, right? Right. That is the latest technology for the highest transmission level voltage that has been achieved. Okay, so you have a step-up transformer that steps up the voltage to that level. Then this is where you have transmission level, transmitting your power that you have generated from the power plant, right? For many miles, let's say 200, 200, let's say to about 350 miles, right? Okay. So the reason why, usually there's a break-even point, like more than 400 kilometers, right? You don't want to go beyond that because for AC transmission, then that is when you experience a lot of significant reactive power losses and resistive losses due to that. So at that time, you need a substation, right? Okay. So this is where the step-down substation comes into play, right? Okay. So let's take an example. You have a 345 kV, right? Transmission level voltage. You've been able to step up from 13.8 kV or 18 kV or 20.2 kV to 345 kV, right? So at this step down sub-transmission level voltage, you've been able to, you're coming in at 345 kV, right? Okay, so at this level, at this station, that is when you can achieve a myriad different level of step down voltage, right? You can achieve 115 kV from here, right? You can achieve 230 kV, right? And to achieve 230 kV, because that voltage is so high, it is always achieved through an auto transformer, right? As you can see here, the turns ratio is very small, right? And for that turns ratio being small, that is usually done through an auto transformer from 345 kV to 230 kV, right? So you are able to achieve 230 kV to transmit it somewhere. Let's say 230 kV going somewhere. You're transmitting that 230 kV to another area for it to go through a step down. Let's say from 230 kV to 69 kV or 230 kV to 115 kV, then utilizing an auto transformer. Okay. Then you can also step it down from 345 kV to 69 kV, right? Here. So at this section, right, we can also have other power generation sources, right, coming, right? And that is why they call it a transmission network, right? Right. You can have other generation, power generation network coming, right? Okay. So at this level, right, you can have industrial facilities, right, that need this amount of voltage, right? Like I indicated, I've been able to step it down from 345 to 69 kV. So this is where industrial facilities come into play, right? And at this level too, that is when you can also tap into this level of voltage, 230 kV or 138, and send it to other industries to step it down to a lower voltage. So this is where industrial utilization of power comes into play. Okay, so I've been able to step down the voltage, let's say from here is 69 kV, right? Right? I'm coming in from sub transmission level, right? Then I go through a distribution level substation, right? From 69 kV to, let's say, 12 kV. From 69 kV to, let's say, 4.16 kV. 69 kV to, let's say, 6.9 kV, right? Okay, so it is at this point that you achieve distribution. And within this distribution substation, you can also step it down further from 12 kV to, let's say, 480 volts. 12 kV to, let's say, 4.16 kV. 4.16 kV to 480 volts, right? Before it gets transmitted to the consumer. So once it gets to the consumer on this pole, right, you have another transformer that steps the voltage from 480 volts to 120, or from 13.8 kV to 480 volts before it gets to the consumer. So this is how the power, the voltage gets to your house, the consumer end. Now, let's talk about the types of substations, right? I think I've given you a little bit of a heads up of and have gone through the different types of substations that we can have. The first one is the generation switchyard substation, right? The second one is a transmission level substation, and I went through that, the flow chart that shows you all the different levels of substations that we have, right from the source, the generation source, the sub-transmission level substation, distribution level substation, then underground substation, right? The underground substations can come in between here, right? We can have a sub-transmission level substation that can be located underground. We can also have a distribution level substation that can be located underground, right? It's all based on the terrain, the environment, right? That is when sometimes they locate some of these substations underground, especially, you know, a very congested city, right? If you have a congested city, highly densely populated cities, right? That is when locating substations underground. And you know, we have a lot of consider a city like New York, right? Very highly density, choked, has a lot of buildings. So cities like that, but your best choice is to locate substations underground. Next is HVDC converter stations, right? Okay, so a lot of these are integrated to offshore and onshore wind farms, right? Okay, so you have a wind farm, right, that basically comes to an AC collection point, then it goes to an AC offshore AC substation, right? You have an offshore converter substation, right, that converts the AC to a DC, right? Then it gets transmitted through a DC cable, subsea cable, until it gets onshore. Then it gets inverted from DC to AC. So here you have an onshore substation, right? That is integrated to this converter. Similarly, for your offshore, you have a substation that is integrated to the offshore converter. So now let's take a little bit of pictorial view of a generation switchyard, right? Okay, so for a generation switchyard, you have the generation source, the generation power plant that is here, right? Then outside this generation is what they call the switchyard, right? So the switchyard has a lot of components, quite similar to a substation, right? But they use it for a lot of switching action, you know, to get the power out there on the transmission line, right? Okay, so we have transformers, we have structures, right? Basically that takes on the feeders from the generator onto the transformer to step it up to transmission level voltage before it goes through all these different tubular bus sections, before it gets onto the transmission line network, before it gets transmitted for various hundreds of miles or hundreds of kilometers, right? At the same time, for this generation power plants, right, you need if you need to bring the generator online, right, you need a startup power, right? So at the same time that you are pushing, you are generating power out there on the transmission line, you should have a redundant scheme, transmission line network that will go through a step-down transformer that will basically step it down to a medium voltage level, let's say 4.16 kV or 6.9 kV, right? They call it auxiliary power, right? So let's say you have a 115 kV coming in, right? Coming in from a transmission network, right? That basically goes through a transformer that steps it down to 4.16 kV or 6.9 kV before it is fed to a medium voltage switchgear with this level of rating, right? And this medium voltage switchgear is what feeds power to all your auxiliary equipment. And just to name a few, what are my auxiliary equipment? Boiler feed pump, heater drain pump, condenser pump, motor, all these motors, and if you have a coal plant, you have pulverizers, right? That basically grinds the coal into different powdery form, right? So basically we have this medium voltage level of voltage that is required by all these auxiliary loads. So for you to start a power plant, right, you need an auxiliary source. So within this switch yard, we have different switches that are in place that basically is integrated to this 115 kV transmission line that is coming from a separate source, right? That comes in here to be stepped down to be fed to all these auxiliary motors and loads that basically helps to complete basically to keep the power plant cycle in place. So now let's talk about transmission level substations, right? On the previous slide, we talked about generation switchyard or a generation substation, right? Okay. So now let's take a look at a typical transmission level substation, right? Okay. So let's take an example. This transmission line is coming from a generation switchyard or a generation substation that has been stepped up from 13.8 kV to 230 kV, 115 kV, 345 kV, 500 kV, 760 kV, right? So you have a transmission line network that is coming in that is rated at any of these voltages that I have listed here, right? So it comes in here, right? This is the entrance of the substation, right? We have a tower structure, right? That basically, the civil engineers basically are the ones that design these tower structures to support the transmission line that is coming in, right? Okay, so at the entrance of the substation, right, we have a lightning arrestor, a surge arrestor. And what is the goal of this surge arrestor, right? Okay, so if a fault should occur on this transmission line, or an open conductor condition, right? What is going to happen, right? Traveling waves are going to be set up, right? Okay, so as you know, traveling waves, how they go back and forth, and so the voltage is amplified due to the short circuit that has occurred, right? So this short circuit is going to basically impinge on this lightning arrestor. Then basically what it's going to do is it is used to protect the equipment that is located in this substation, right? Other than that, the traveling wave is going to go inside the substation and basically fail the equipment, right? So that is why we have a lightning surge arrestor right at the entrance of the substation. its goal is to basically protect the equipment that are located in this substation. When it is in normal operating condition, right, it has a high impedance. It is connected in a shunt configuration, right, connected from line to ground, right. And when it is in operating and it is in normal operations, right, only leakage current flow, very small leakage current in the form of milliamps, right. As soon as it senses an overvoltage condition based on its rating, right, it clips the voltage, right. Once it clips the voltage to the required clip voltage, it changes from a high impedance operating characteristics to a low impedance characteristics so that it can conduct the discharge current from the short circuit to ground. Secondly, if you have a lightning impulse due to a lightning strike, right, that occurs from a lightning surge, right, and an overvoltage condition is created, right. Once it senses that overvoltage condition from a lightning striker, basically it changes from a high impedance operating characteristics to a low impedance, and basically shunts the discharge amps, kiloamps to ground to protect the equipment that is in this switchyard. Okay. So this transmission line network, let's say we have 765 or let's say 345 comes in here, right? Then along this horizontal path, it's a tubular bus, right? In a bus arrangement, right? The substation has different configurations of bus arrangements, and I'll go through the different bus arrangement for a substation in a different presentation, right? Okay, so this substation has main 1, main 2, right? Okay, so the main bus is this one, the first main bus. The second main bus is this one, and this one is an auxiliary bus, spare bus. Okay, so as you can see, the feed comes in here, right? Then it goes through this tower structure. Then there is a drop-down conductor that goes through a disconnect switch. Then from the disconnect switch, there's a riser that comes in here that connects this bus, right? So that you can feed power and voltage to energize this bus. So this bus is in a 3-phase arrangement: phase A, phase B, phase C arrangement, right? In this horizontal arrangement. Okay. So in between auxiliary bus and second main bus is a circuit breaker right here. And on this side of the circuit breaker is the disconnect switch, right? Disconnect switches basically allows you to isolate the equipment after you have de-energized the equipment to perform maintenance. Right? Okay. So from here it goes through another structure, tower structure, right? Then it gets fed 3 phases, right? This 345 kV line comes in. Then it goes through this tower structure. Then we have drop-down conductors, right? That is fed to this bus, second bus, right? The second main bus to energize this second main bus. So this second main bus, like I indicated, phase A, phase B, phase C. Okay. In between the second main bus and the first main bus is another circuit breaker, right? Remember, I told you that the purpose of this circuit breakers is basically it performs that switching function, right? So it allows you to energize basically power from here to here, from here to here, right? And basically energize these buses in between based on the switching function that you have. Right? So from here we have risers, conductors that basically gets integrated to this bus. on the first main bus to energize this bus. On this side, so this is basically the very high voltage side, transmission level voltage. If it is a 230 kV, 115 kV, 345 kV, 500 kV, 765 kV, this is the transmission level voltage at the substation. Okay, as you can see, you can see another transmission line network coming in from here, right? So redundancy is usually implemented in the design of substation, right? Okay, so that if there is a fault on this line, right, this line can be de-energized and this line can be energized to be able to continue to provide reliable power to the customer. So that's how redundancy is built into the design of substation. Okay, so at the same time that I'm coming in with all this level of voltage, 115 kV, 230 kV, 345 kV, 500 kV, 765 kV, there are outgoing feeders, right? As you can see over here, to another city, right? Many miles, 150 kilometers, 50 miles, 100 kilometers, 200 kilometers. So these are outgoing lines, transmission line, same voltage, 115 kV, 230 kV, 345, 500 kV, right? To another substation to perform the same function as you are seeing over here. So this is how we basically build substations from city to city and transmit the power to the consumer. Okay. So on this side is sub-transmission level voltage, right? We have the transmission level voltage here and the sub-transmission level voltage. And for this design, they are all in the same substation vicinity, right? Okay, so I'm able to basically get 115 kV, 230 kV, 345, 500 kV, 765, whichever voltage your design is, right? Then for this sub-transmission level voltage, similarly, I have a main and transfer bus, auxiliary bus, right? Spare. Redundancy has been built into it. Then I go through a step-down transformer from 115 kV to 34.5, 115 kV to 12 kV, right? So once I achieve that level of voltage, then I can go out to distribution level substation somewhere else. At the same time, I should be able to transfer the same voltage that is basically step down, right? If it is 13.5 kV, 12 kV, 34.5 kV, somewhere else to be step down in another city. Now let's take a look at this nice picture, right? Okay, so remember I made mention that at the substation, if you have a substation, right, you need to protect the substation, right? And lightning surge arresters are utilized to provide that purpose, right? Protecting the substation, right? These surge arresters are made from metal oxide varistors, right? They are gapless. They call it gapless, right? And it is made inside. These are discs of MOVs, right? With insulation around it. Okay, so I think I explained to you in the earlier slide that under normal operating situation, right, we have a transmission line that is coming here, right? It is coming here. It is coming to the substation, right? And it gets connected to the top of this. Under normal operating condition, right, this offers a very high impedance, right? We have a 115 kV, 230 kV, 345 kV, 500 kV, 765 kV coming in to the substation, right? Under normal operating conditions, this metal oxide surge arrestor offers a very high impedance to ground. So only leakage current flow in milliamps, right? Due to the linear characteristics of these semiconductors that is inside these surge arrestors. And depending on the level of voltage, as you can see over here, we have many stacks of this that has been connected together. Stack 1, stack 2, stack 3. And there's a little bit of stack there, right? It is all based on the level of voltage that is here, right? Okay, so 105 kV might have, let's say, 2 stacks. 230 kV might have, let's say, 3 stacks. 345 kV might have more than, let's say, 4 stacks. Right. So that is how the stacks are built. They are based on the level of voltage, the line-to-line voltage and the line-to-neutral voltage to achieve the maximum continuous operating voltage of the surge arrestor. Okay. So once we have a lightning strike, okay, in close proximity to the substation on the transmission line, right? And let's say on top of the transmission line, right, we have a shield wire, right? And the goal of the shield wire is to protect the phase conductors, right? Okay, so sometimes, these lightning strikes can come at an angle where basically the shield wire might not be able to protect the phase conductors, right? So once it hits the phase conductors, they form a traveling wave and try to enter the substation, right? So once it does that, it is the surge arresters that are at the forefront of the substation to protect all the equipment that is located in the substation. It protects the transformers, it protects the disconnect switches, it protects the circuit breakers, etc. that is in the substation. Right? So that explains what the surge arresters that are located right at the forefront at the entrance of the substation, because before it gets to the transmission tower that is located at the front of the substation. So I think I explained this transmission level substation in the earlier slide. Okay, so once basically we get this is our main one, our main two, this is our auxiliary bus, right? Okay, so like I indicated, redundancy is always built in the design of substation. So we have transmission level substation voltage here, and these are all the buses, right? Phase A, phase B, phase C. These are made from aluminum. They are tubular bus, right? In a round configuration, and the civil engineers basically design these buses, and basically they are designed to be able to carry continuous rated current, and also to withstand short circuit current, the maximum, the asymmetrical, and the resultant dynamic, electrodynamic forces, electromagnetic forces, right? Because if you have a fault, right, basically what these tubular buses see is basically they encounter that force, and basically it shakes them. So the goal is for them to be very rigid and to withstand that electrodynamic forces that are created due to peak short circuit that occurs during the first quarter cycle of a fault signal. On this side is basically your subtransmission level voltage that basically steps the voltage from here to voltage that can be sent to a distribution substation. Okay, so this picture basically basically gives you a much deeper, On the high voltage side, let's say 115 kV, 230 kV, 345 kV, 500 kV, or 765. You know, depending on your level of voltage for your design, right? Okay, so you're coming in, right? Remember I made mention that right at the entrance, right? These are the surge arresters. Yeah, that protect the substation, right? Make sure that you don't have any extreme over voltages that will end up destroying the equipment, right? Okay, so that is part of your installation coordination studies that is done during the planning stage of the projects, right? Okay, and underneath this substation towers, right? It's basically this is connected in a shunt configuration. So these are CCVTs, right? Okay, either VTs or CCVTs, right? Okay, so VTs for a high voltage substations are the inductive type of voltage transformer, right? And this is usually connected in a shunt configuration. But at voltages of greater than 115 kV, it is much cost beneficial and economical to utilize a capacitive coupled voltage transformer. The difference between the the inductive type of voltage transformer and the capacitive coupled voltage transformer is that basically this one this voltage transformer utilizes an inductive element, an inductive transformer, and it is wound, and it basically the enclosure has oil in it. Basically, that and the transformer, that little transformer, basically steps down the voltage to either 115 or 69 volts to be used by mirroring and protective relays, right? Okay, so this one is basically providing voltage signals to your mirroring circuits and also your protective relays for it to basically monitor activity in the substation. On the other hand, capacitive coupled voltage transformers or capacitive voltage transformers, right? Okay, utilizes, because of the high voltage, right, that it basically it's applied. It utilizes capacitors, right, to achieve a voltage divider. So we have a 115 kV or 230 kV, right, or 345 kV, right, 500 kV, 765 kV, right? Okay, so we have a capacitance, right, that has been arranged in a voltage divider configuration to achieve a lower voltage, right? Okay, so if I have my transmission line coming in here, I have a 115 kV. So the goal is to basically achieve, let's say, 2 kV on this section or 10 kV on this section, right? Then I can feed this 10 kV to an inductive transformer that is immersed in oil that steps the voltage down from 2 kV to 69 volts, or line to neutral voltage, or 115 kV line to line voltage to be used by our protective relay or mirroring elements. Okay. So on this side, as you can see over here, those are insulators, right? Basically, that protects the conductor from ground plane. Remember, the tower structure basically, you know, is a ground plane, right? So the goal is that these conductors have to be protected, you know, from ground plane, right? So underneath is a jumper, right? That basically connects to this side. So on this side is your insulators, right? And on this side is your insulator, and in between is your jumper. That basically helps, is installed to preserve the continuity of the circuit, right? Okay, so these insulators are basically, you know, designed based on the level of voltage, the amount of voltage, right? You know, the line-to-line voltage. That is how. So the number of this is based on that voltage that I was indicating. Right? Okay, so from here you come in here, and similarly we have insulators on this side, right? Then we have vertical insulators on this side, right? Then we have a drop-down conductor, right? Okay, it drops down, right? Then it goes through disconnect switch, right? And it comes in here to energize this auxiliary bus, right? So this is the auxiliary bus. Remember, this is main bus 1, main bus 2, main auxiliary bus. Then in between this tower structure, right, and this main bus 2 is a circuit breaker, right? So you should have a condition to be able to switch in and out in between these buses, right? So and on this side is a disconnect switches, right? Okay, remember, once you de-energize the circuit breaker, right, you should have a way of opening and for maintenance to be performed, right? So that is for safety of our personnel that is working in the substation, right? Okay, so then we have this tower structure, right? Okay, so on this side of the circuit breaker bushings, right? Phase A, phase B, phase C. Then on this side, incoming, outgoing section, come here, and it goes up, right? Okay. Then basically to energize this section. Then in between here and here, we also have circuit breakers that allows you to switch in and out in between main 1 and 2. Next is another bird's eye view. Basically, that gives you, like I indicated, that in between, this is main 1 bus, main 2 bus, and auxiliary bus, right? And I may mention that this one is a redundant feeder, right? And we have the main feeder coming from this end, right? Okay, so in every substation design, redundancy is very important, right? Okay, so that if there's a fault on this line and this line has to be taken out for maintenance, right? Then we have another source that we can basically use it to energize this bus to keep continuity of power and basically resiliency of the power system network, right? Okay, so in between main bus 1, main bus 2 is a circuit breaker, and on each side disconnect switches. That helps you after you have de-energized the circuit breaker. You need to basically open this disconnect switch on this side and open this disconnect switch on this side. Similarly, to energize the bus, basically you close the disconnect switches, right, on this side, and close your circuit breaker, right? Okay, so phase 1, phase 2, phase 3, or phase A, phase B, phase C. Phase 1, phase 2, phase 3, phase A, phase B, phase C, right? Okay, so this also shows another picture that shows you in between the auxiliary bus and main 2, right? We have a circuit breaker arrangement that helps you to switch in and out, right? And disconnect switches. Okay, so another picture, right? Okay, that shows much deeper picture that shows you arrangements in between main 1, main 2, right? And the circuit breaker in between them that helps you to switch in and out, right? And disconnect switches on both sides of the circuit breaker, right? Okay, so and also outgoing lines, right? Outgoing lines, basically going to another city post. So this picture also shows you a little bit of much detail, right? Okay, so this section, it's your high voltage substation, right? Very high voltage transmission level substation, right? Okay, so you are coming in, right? Then from there, basically, you are going out, right? Okay, so you are going out to the sub transmission substation, right? Through step down transformers. Okay, so now we've been able to basically leverage on 115 kV, 230 kV, 345 kV, 500 kV, 765 kV, right? From this very high voltage substation, that is a transmission level substation that is coming, right? Okay, so, and we've been fortunate enough to also leverage this transmission level substation in close proximity to the transmission level voltage. So it goes through a step-down transformer, right? It steps it down to, let's say, 69 kV, 34.5 kV. You know, different level of voltages. You know, if the higher your transmission level voltage, you know, you can go a little bit. You know, let's say if it is 765, then I can go like 230 kV or 115 kV, right? To send it out there to another substation, right? Okay, so within this sub-transmission level voltage, right? Okay, so we can also have outgoing feeders, right? We can also have redundancy in it, you know, and basically outgoing feeders are to another circuit, you know, to step it down to another voltage level. So this is another good picture that shows you how the bays are arranged, you know, and this is a circuit breaker and disconnect switch arrangement that basically helps you to integrate between the buses, bus one, main bus 2 and auxiliary bus, main bus 1, and in between that, you know, all this disconnect switches as well. So now let's take a look at this picture, you know, and this basically it's a city, right? Okay, so the difference between those are instrument transformers that you'll find at the transmission level substation, right? Okay, so the difference between those instruments is a CT is connected in series. So if you see a series arrangement, right, that tells you it's a CT, right? If it is a shunt arrangement, right, it is connected like this, then it is a big T, right? CTs are connected like this, right? Okay. In series with a bus. So as you can see over here, this is a CT. So this is a high voltage inductive type of CT, right? Okay, so it has basically windings that are immersed in oil, right? Okay, so basically it is able to step down the current basically from let's say if it is let's say the rated current is let's say 4,000 amps, right? You're able to achieve 5 amps or 1 amps for the mirroring circuit or your protective relays, right? Okay, so as you can see over here, this is your terminal box, right? Okay, and also sometimes no, this one is the connection from the high voltage terminal and outgoing to this circuit breaker over here. So the terminal box is for the secondary wire is usually located at the base of the instrument transformer, right? Okay, so this one is basically porcelain insulator that basically protects the live component from ground plane. You know, so like I indicated that, you know, this porcelain insulator is made, is, you know, it's been formed, it forms a zigzag configuration, right? And the goal is basically to increase the clippage distance due to contamination, right? This is an air insulated substation, right? It is exposed to the elements, right? If you have industrial facilities or any other, you know, pollution facility that is emitting a lot of pollutants into there, these pollutants will basically fall on this surface, and as periodically it's going to build up that contamination, and you know, and basically leakage current will start flowing. Okay, so what it is doing is basically the way it is shaped is to stretch, you know, and increase the clippage distance. Right? Okay, so inside this enclosure, it's oil filled with the winding and the core, right? Okay, so the primary winding goes through like this, right? It's a single conductor, right? So this is what you see. This is the primary conductor that goes to the city, and the city has a core, right? And on the secondary are many turns, right? Many turns, right? That is basically, you know, 5 amps to achieve the 5 amps or 1 amps, right? That goes out to this terminal box, then it goes to your protective relay elements, right? Okay. On this side is a circuit breaker, right? Okay, so this circuit breaker is called, you know, live tank, of circuit breakers. There are two types of circuit breakers that high voltage circuit breakers that you see. We have dead tank circuit breakers and live tank. So this is a typical of a live tank circuit breaker, and inside this circuit breaker, this is the interrupting chamber, right? This one is just a support insulator just to protect it from ground plane, right? So this interrupting chamber has SF6 gas, right? So we have a stationary contact, we have a movable contact inside, and inside this is SF6 gas utilized to quench any arc that can occur during opening and closing of the circuit breaker. Then again, these are basically buses, right? Okay, tubular bus, right? Okay, made from aluminum conductor. Another arrangement, it's a GIS, right? Okay, so in a substation environment, you can have a hybrid technology that is air insulated switch gears plus gas insulated switch gears, forming a hybrid configuration, right? So this is a typical example of a hybrid configuration where you have gas insulated buses and gas insulated switchgear, right? Okay, so these are all filled with SF6, and I think in one of my previous presentation, these are apparatus bushing, right? Inside this is SF6 gas, right? As an insulating medium, right? Inside this is SF6 gas as an insulated medium. Inside this is your bus arrangement, right? Okay, inside this is filled with SF6 gas, right? As an insulating medium, right? Okay, so on top of this one is a grading ring. We call it a shield ring or grading ring, right? Okay, so let me explain to you why we utilize that. Okay, so we have a high voltage connection, right? It's like a breakpoint, right? Interface, connection point, right? Okay, we have air, we have SF6, right? Then we have this insulator apparatus, right? This portion. Okay. So at that interface, right, due to the high voltage, right? Okay. So let's say if we have, let's say 345 kV, right? There's something they call electric field, right? And what is electric field? It's voltage over distance. So as you can see over here, right? The connection point is very small. So if you have that 345, right, and you have a very small connection point, minute, right, the electric field is going to be very high in air, and it's going to break down the insulation around here and destroy this porcelain insulator. So we utilize a grading ring, as they call it, grading ring, to grade the electric field that is found in this area, right? So what we are doing is we are basically forming different sizes of ring, right? Okay, so we are stretching, increasing the D over here, right? The electric field is voltage over distance, right? So we are increasing the distance from a dot, which is just a connection, right? There's a transmission line coming in to connect to this connection over here, right? We're increasing, stretching the distance, D. So as we increase this distance, the electric field decreases. So that's how we are able to protect their porcelain insulation from damage, and also preventing corona action due to the breakdown of this surrounding insulating air, right, due to high electric field. Next is another beautiful picture of a transmission level substation, right? Okay, so I explained to you in the previous slide, this is an instrument transformer, right? Okay, and this is how you always distinguish between a current transformer and a voltage transformer. A current transformer is connected in series with the conductor, right? Whilst a voltage transformer is connected in a shunt configuration to ground in parallel with the conductor. This one is a VT. Right? So as you can see over here, right, we have the conductor coming, conductor come out, right? So one single turn of conductor, and the secondary. So the primary turn is just a single one, and the secondary is many turns wound on a core, right, to achieve either 5 amps or 1 amp that is needed by your mirroring circuit or your protective relay circuit. Right? So your mirroring circuit, definitely you need to know your billing, right? Okay, and basically charge the customer, right? Okay, so that is how your mirroring circuit comes into play. And your protective relay signal is basically to protect, take the measurements and basically, if there's a fault condition, basically protect the transmission level substation. Next is circuit breaker, right? Okay, so this is called a support structure, right? So these structures are basically, like I indicated, these structures are all coordinated with the civil engineer, right? Discipline civil engineer. He or the person, she, basically the person evaluates all these support structures to make sure that it can withstand. And also they collaborate with the manufacturer of this circuit breaker. Okay, so this is remember I made mention that there are two types of circuit breakers, transmission level circuit breakers, right? And these are basically live tank and dead tank, right? Okay, so this is a typical example of a live tank, right? So this support insulator, very rigid, right? Basically provides us isolation from this live component inside, right? This is basically where the interrupting chamber, right? We have a stationary section and we have a movable section, right? And this section is filled with SF6 gas. So the SF6 gas, it's an arc quenching medium, insulating medium, right? Inside. Let's say if you're operating, closing the contact, right? You have a stationary contact that is always stationary. We have a moving contact. If the contact is going to basically get in touch with this moving contact during the close operation, right, an arc can fall. Or if, let's say, the circuit breaker needs to open due to an opening action, or let's say due to a fault interruption, the pattern, the moving of this movable contact can create an arc. And if this arc is not extinguished in a timely manner, it can form a basically a restrike voltage. Basically, they call it transient recovery voltage. Can create another high voltage and allow basically a conductive element to flow, whilst the circuit breaker is even in open position. Next are basically structures, right? Basically that supports the transmission line coming in, going out, right? Remember, we have a transmission line coming in, going out, right? And also going to, let's say if you have a sub transmission, it goes out to other substation for step down, right? Okay, so these are all disconnect switches, right? Disconnect switches basically that allows you to isolate the equipment after you have de-energized it. You need to de-energize it because this one is basically a no load disconnect switch. The circuit has to be de-energized and basically open it for, let's say, maintenance to be performed on the equipment. So now let's move to the sub-transmission level, right? Okay, so the sub-transmission level, let's talk about the 69 kV voltage, right? Okay, so Remember, I made mention that there are two types of circuit breakers, right? So at the transmission level and at the sub-transmission level, we can have a live tank circuit breaker, and I showed you and explained how the live tank circuit breaker looks like and how it works. This one is a typical example of a dead tank circuit breaker. So this circuit breaker, the control panel is right here. Let's look at here, right? Okay. Then this one are the apparatus bushing, right? So I'm coming in here 69 kV, right? And I'm going out 69 kV. Phase A, phase B, phase C. Phase A, phase B, phase C. Right? And I'm coming in like this, right? So inside this interrupting chamber, below this is an interrupting chamber that is filled with SF6 gas at the required pressure. Okay, so this SF6 gas basically is an insulating medium, right? And an arc quenching medium. If you have an operating of the contacts, we have a stationary contact, we have a movable contact, and we have an arcing contact, basically that helps basically to extinguish the arc as fast as possible. Okay, so this conductor, like I told you, goes through this. This is the apparatus bushing, right? And inside this, we have SF6X as an insulating medium. And I explained to you, this is a porcelain type of external bushing, external insulator. And for this external insulators, we have two types. We have the porcelain, right? And we have the polymer, right? The porcelain is made from pottery material, clay material, right? Okay, and it is very rigid. And one of my presentation, I explained to you the differences between the two types of technology, the two types of materials, porcelain and polymer. And I also have explained to you several times in different sessions the reason why we have this zigzag configuration of the apparatus bushing is to increase the leakage current path to ground, to prevent a flash over due to the buildup of leakage current. This type of porcelain insulator basically lacks hydrophobicity, right? It lacks the capability to repel contaminants. It allows contaminants to build up on it easily, comparably to a polymer, right? Polymer insulators are made of silicone rubber, right? Those sheds are made from silicone rubber, right? And I explained to you the attributes or the advantages of the silicone rubber. The silicone rubber insulator has an excellent capability, hydrophobicity. It means that it repels contaminants. It forms, if contaminants and water forms on it, it forms beads, right? It does not form a continuous film like porcelain, this one that you have seen, which basically enhances, propagates the formation of leakage current to path. On the other hand, because polymers forms beads, it prevents the formation of a continuous film that can enhance the formation of leakage current flowing to ground. And I also explained to you the disadvantages. Because it is flexible in nature, it can basically break easily if birds with long beak poke on, right? And the great advantage of this is its mechanical strength. But if you have somebody, hit it with a stone, then it's going to break and shake. And elements of the water can get it into the insulated medium and degrade it. Okay, so that is the difference. Okay, so we have 69 kV on this side, right? Okay, we have 69 kV coming in, goes through this circuit breaker. And the purpose of this circuit breaker is to switch incomer with outgoing feeder to isolate or energize incoming feed with outgoing feed, right? Okay, that is the purpose of this circuit breaker. On each side of the circuit breaker are disconnect switches. So there are many types of disconnect switches, right? Okay, and this one is a vertical grid disconnect switches, right? And it is mounted from ground plane on a pedestal. This is what they call a pedestal, right? Okay. So what you're seeing here is the mechanical linkages, right? Mechanical linkages, right? That helps to they are linked together to open and close, right? Okay, so they are operating. The operator comes in here and steps on this ground mat. Okay, so this ground mat is to prevent static, charges, shock, and voltages build up, right? So if the operator is supposed to operate this disconnect switch, let's say open this disconnect switch or close this disconnect switches, the operator, as required by the safety guidelines, is to stand on this ground mats. They call it ground mats, and operate it, right? So because in the substation design, right? Okay, there's something they call F grade design, right? You have a ground mat that is below the surface of this substation, right? Okay, so underneath this is on top of this substation are all this equipment, right? Okay, so the ground cable is bonded to this equipment, right? Then to the equipment, you have a ground lead that comes in here and goes through a ground rod that is connected and welded to this ground mat. So this ground mat is in a grade formation, right? Called earth grade. Okay, so during the design of substation, right? Okay, there's something they call ground potential rise. Studies are performed based on the resistivity of the soil below the substation, right? Below the substation, there are different layers of soil, right? So your geological engineer basically does all the soil analysis, right? And your civil engineer as well, to determine the resistivity of the soil below that and the thickness of the soil below that. Then, based on the short circuit analysis that is done for the whole substation grid, right? The west fault scenario is determined based on different configurations of the substation to determine the worst case fault current. So based on that, the ground potential rise is determined to identify that your step potential clutch voltage is within the allowable. So that is why this ground mat is provided. Okay. So as you can see, on the surface of substation, we have rocks, we have gravels. All these are added to add an additional layer of resistivity. They call it surface layer resistivity, right? If they do all the analysis and found out that the step and touch potentials, right? Step and touch potentials, right? Okay, so the step potential, right? If your leg is right here, right? One leg is here, another leg is here. If they are separated by 1 meter, right? The voltage difference is what they call step potential, right? It has to meet a certain criteria based on IEEE standard 80, right? And there's something they call touch potential, right? Okay, so if let's say the operator is standing here, right, and has his hand touching this equipment, right? The ground potential between here and the ground mat is what they call the touch potential. So that one also has to meet a certain criteria, right? So that's why they do all these studies and identify, and based on that, if they find out that they need to add additional surface resistive layers, so that's when you go to the substation, you see all these gravels and rocks and all those things on the surface, right? Okay. Right. Then on the side is your horizontal tubular bars, your rigid bars made from aluminum, right? So I explained in the previous class that the civil engineers do all the analysis. The system studies people basically provide an input of the short circuit studies to the civil engineers for them to design these tubular bars to withstand the electrodynamic forces that are created due to a short circuit scenario, the worst short circuit that these buses will see. So I have explained on the side, right, and explained everything to you. So on the side is the tubular bars, and basically explain to you on the side, right, as you can see over here, is another arrangement. They call it the hook switch, right? This is a vertical mounted disconnect switch, right? Basically in a vertical open and close mode, right? And most of it, is called a hook switch, right? Okay, so I'm coming in 69 kV, right? Okay, so on this side, I should be able to isolate that feeder, right? Utilizing this hook switch from the incomer, right? Then on this side, on the feeder end, I should be also isolate this section utilizing this disconnect switch, right? So if you have a circuit breaker, right, a disconnect switch on both sides, if you de-energize this circuit breaker, right, then you open this disconnect switches on both sides. It's more of a safety, okay, maintenance and safety. Similarly, for you to energize, you have to close both, right, before you energize, right, because it is a no load disconnect switch. Next, it's basically, as we are coming on the tubular bars, right? Okay, from the previous slide, right? Then I come to another arrangement, right? Okay, so this one is a vertical break disconnect switch, right? A disconnect switch, no load operated disconnect switch that can be open and closed. Its goal is isolation after the de-energized equipment, right? To be able to separate the side from the side, right? We have a feeder going this way, so I should be able to separate this section of the bars to the, right after, the other side of the circuit breaker. Remember, there was also another disconnect switch side. So I should be able to, for maintenance purposes, for safety purposes, I should be able to isolate after I have de-energized the bars. Right? So that's how we have these disconnect switches come. Okay, so on this side rises, right? conductor risers, right? Okay, so just tagging on this tower structure, right? So this tower structure is a typical structure, tower structure. This looks like an H frame or A frame type. Okay, okay. So I have the risers coming in here. Then I have my conductors coming in here. Then I come to a step down transformer. Okay, so as you can see over here, a step down transformer. I have my radiator over here. Then I have a drop down conductor, right? Over here, I have a cable conductor riser, right? I'm trying to tag on this conductor over here. But here, I have to come down, drop down, right? So I drop down and I come to the bushing, the transformer high side bushing over here. On the high side are surge arresters, right? I told you that, as much as if we have a surge arrestor at the entrance of a substation, be it a transmission level substation or a sub-transmission level substation, at the same time we have a dedicated equipment level surge arresters. This is the insulation coordination is achieved utilizing insulation coordination studies. So that is how the number of surge arresters are determined. Okay. In addition to that, the insulation system of this transformer is designed to withstand lightning and switching surges. Okay. So, as you can see on top of right here, what is this? Okay. This is an air core reactor. And you might want to ask, what is the purpose of an air core reactor? And why are we using? Okay, so sometimes when substations are being designed and need to be built, right, as part of the planning stage, system studies are performed. Load flow, short circuit analysis studies, protective relay coordination studies. Okay, so when they do the protective relay and the short circuit studies, right, then they find out that the available short circuit that is flowing from the source, from the utility source, right, coming from the previous slides that I showed you, where that circuit breaker interfaces, right, coming from the source, the 69 kV source, right, it's so high. MVA short circuit, and it's usually given in 3-phase or single phase, right? The utility will give you the maximum and the minimum, and it can also be given in fault current, 3-phase or single phase. So if the short circuit level is so high, that means that you have to design a switchgear that can withstand a higher short circuit current. It means that the horizontal bars, the bus system of your medium voltage switchgear everything has to be big to withstand that. The switchgear equipment itself has to be big. And what does it translate? That means cost. Your cost is going to be high. So how do I mitigate that incipient cost that is cropping in? That amount of cost that's cropping. So I have to come up with a strategy, a design strategy of limiting the fault current from the source. So that is when I utilize this reactor to limit the amount of fault current that is going to flow from the source before it gets to the transformer. Though the transformer itself has an impedance, right, that is going to add to this reactor to limit the fault current more, so that I can achieve a smaller fault current here and be able to design and manufacture my medium voltage switch here at a lower cost and lower footprint, lower dimensions. So that is the reason why this air core reactor is utilized. Okay, so on this side are disconnect switches, right? Okay, so you have a disconnect switches that allow you to disconnect this side from the side for maintenance purposes and for safety purposes, right? Okay, after you de-energize the equipment. Next, let's talk about distribution level substation, right? Okay, so for distribution level substation, same philosophy, right? Okay, so this what you see over here are, they call it MUST, lightning arrestor, that are located on top to protect the substation from lightning strikes and protect the equipment as well, right? So the number of lightning masts or lightning arresters that is achieved is based on system series, right? Okay. So this tower structure is called H-frame. As you can see, it is in the form of the H letter, right? Okay. So on top of that are income. As much as you are protecting the whole substation based on the arrangement of these lightning arresters, we have surge arresters too, that basically protects the equipment at the entrance of the distribution level substation, right? Okay, so there is a difference between lightning arrestor and a surge arrestor, and let me explain the reason why. A lot of people get it confused, and sometimes utilize the same word instead of utilizing an arrestor for an arrestor, they utilize a lightning arrestor for an arrestor. Okay, so this one is a surge arrestor. Okay, so this surge arrestor is made of, remember I told you that metal oxide varistor, right? This is a gapless surge arrestor, and has metal oxide varistors made in the form of a disc inside it, right? And inside it is a fiber insulation layer, and outside is a let's say porcelain or polymer external insulation. Okay. On the other hand, this one is a lightning arrestor, right? Okay, just like the one that you have on the roof of your house, right? This one is just a conductor, basically that it's pointed upwards, basically for and reaches out to lightning strike faster and basically takes it to ground quickly. So that is the difference between a lightning arrestor and a surge arrestor. Right. Okay, so on this side is disconnect switches, right? And your tubular bus arrangement, right? And these are all connections that support insulators that protect the live tubular buses conductors from ground plane, right? Then similarly, we have this arrangement. These are disconnect switches, as you can see over here. Vertical breaker disconnect switches, right? Before it gets to this power transformer, right? Okay, so this power transformer basically steps the voltage down, let's say from 69 kV to 6.9 kV or 4.16 kV or 12 kV, right? Then on this side, on the low voltage side of the transformer, is a voltage regulator. Okay, so what is the purpose of the voltage regulator, right? Okay, The low voltage side of the transformer is basically interfaces with the load, right? And that is the customer end, right? Okay, so as the customer, load basically goes up and down, there has to be a way of regulating that load. Because if it goes up, if the load goes up, the voltage is going to go down. If the load comes down, the voltage is going to come up, right? So if you don't implement a means of regulating that voltage, then basically you're going to have a power quality problem. Right? So we have voltage regulators that are connected in each phase, phase A, phase B, phase C, on the low voltage side, feeding to the customer to regulate the voltage on the low side of the customer. Okay. So this one is a typical vacuum circuit breaker on the low voltage side that feeds the customer, right? So we can have this feeder comes in and goes out, to another substation similar to this one, to basically perform another step down, right? Then on the other hand, it can come in here, step it down to a lower voltage to the customer. So this is another arrangement from the top of the structures, right? Okay, so this structures look like an A. Sometimes they call it a frame, okay? So on top of this, basically you have like a main bus and a transfer bus, right? Yeah. So a main and transfer auxiliary bus scheme, right? So the main is usually is the bus that is energized most of the time, right? Okay. Then when you have to perform maintenance on the main bus, then that is when you incorporate the required switching to, and also changes in the protective relay settings to accommodate transfer to the auxiliary bus scheme. So this is another picture from a different angle, right? Okay, so that shows you the incomer goes through disconnect switches, goes through bus arrangement, tubular bus arrangement. These are all support insulators, right? And like I indicated, the support insulators are basically to provide a ground plane protection for the live conductor, right? Okay, so this one is a ground plane, and we are using this insulators, and I indicated, I showed you that this are porcelain type bushing, and they are designed. The number of this is based on the voltage level, right? Okay, so this one is a pole-mounted transformer. This one is probably substation auxiliary power that so basically it goes through that and basically step down to, let's say, 230 volts, 120 volts, or 480 volts to be used for the substation power. So this is also from a different angle. It shows you the bus arrangement, the tubular bus arrangement, how they are arranged, and basically the support insulators, as you can see over here. And this one is basically a pedestal, basically that is providing a ground plane protection for this distribution type of support. So the load end is what comes into your house, right? From the distribution end substation that I showed you in the previous slide, right? From there, I told you that it steps it down from, let's say, 12 kV to 480 volts, right? Then it comes to your house. Then you have a pole mounted transformer that is on the pole that steps it down to, let's say, from 13.8 kV to 480 volts, right? Okay, so you're coming in 13.8 kV or 12 kV or whatever, 38 kV or whatever voltage that you have, to steps it down to 480 volts. Then it comes to your household, right? Okay, so sometimes you can have other transformers that will step it down from 480 volts to 120 volts, and those transformers should either be pole mounted or located on the platform on the foundation in your neighborhood. Next up slide, it's basically substation equipment. Like I indicated, the substation itself has a lot of equipment, right? Okay, and we'll go through all the different equipment components that consist of substation and the layout. Equipment selection is one of the most critical stage as part of substation design. And basically, this is done after the design stage, as part of the planning stage. And because some of these equipment are long lead items, basically priority is given to it at an earliest stage of the planning stage. Okay, so this is a power transformer, right? Okay, so as you can see it as a transmission level voltage, its goal is basically to step down the voltage from, let's say, 345 kV to, let's say, 115 kV or 69 kV or, let's say, 12 kV, right? Okay, so that's what this transformer does. Okay, so as you can see over here, these are bushings, right? Okay, so we have the incomer over here, and basically this one, depending on the amount of current, right, and the voltage levels, this one is utilizing two conductors, right? Okay, so based on the design, it was found that two conductors will be better, so that's why they have two conductors in parallel, in that they are sharing the current, right, instead of one conductor. Okay, so this is the bushing, right? Okay, so it comes in here, then the conductor goes in here, then it goes to the high voltage winding, which is the outer winding layer. Then inside this transformer is the low voltage. Then inside that is the core, right? So this one is just a single link, phase A. Then similar one for phase B, phase C. So this is what is inside this transformer. This is what they call the turret, right? Turret. Okay. So this is where all the bushings are located, and where all the CTs are located, right? So the CTs are located here, to be used for mirroring and protection, right? Okay. On this side is a lightning arrestor. As you can see over here, this is also another lightning arrestor, right? Okay. And I explained to you what this means, right? Okay. The grading ring, right? The grading ring, right, is to grade or gradually reduce the electric field that is created from these connections, which can break and ionize the air that is surrounding the connection over here, and can also destroy the porcelain insulator. So that is why we add this grading ring to this arrestor. Okay, so another substation equipment, high voltage circuit breaker, right? Okay, so I told you that there are two types of circuit breakers that you can see at transmission level substation and sub-transmission level substations, right? Okay, so this one, the first one is a dead tank substation, and I've explained in the previous slide how this circuit breaker works. The next one is basically close to it is the live tank circuit breaker. And this one is the dead tank circuit breaker, right? And I explained to you that this is the interrupting chamber, right? The live port, right? And this one is just a supporting son of support insulator that protects this live component from ground plane. And for this dead tank circuit breaker, okay, you have the feeder comes in, right? Let's say if it is a 69 kV, right? It comes in here, it goes in like this, right? And it comes in here. This one is the interrupting chamber, right? Okay, so interrupting chamber, we have a stationary part, we have a movable part, we have an arcing contact that is here, right? All of this is filled with SF6 gas, right? That is filled at the right pressure. Then it comes in here, the conductor comes in here, then it goes up, right? For all phases, phase A, B, and C. Okay, so one of the buildings or enclosures that you find as part of the substation equipment, it's a metal clad switchgear. So this is an example of a metal clad switchgear. And for switchgears, there are two types. We have the metal clad, which is this one. Then we have the metal enclosed, right? Okay, so the metal enclosed, it's basically more of an IEC and a few ANSI, right? But the metal clad is mostly ANSI, North America, right? Okay, so as you can see over here, the name speaks for itself. metal clad. It means that, basically the external is clouded, right? The external medium, or basically, it's clouded, and also inside the medium voltage switch here, basically it's compartmentalized, right? Okay, it's compartmentalized in that, and also live components basically have insulation on it. It is not exposed, right? So that is the difference between metal clad switchgear and metal enclosed switchgear, right? Metal enclosed switchgear, you see that some of the live parts are exposed and it is not compartmentalized, But metal clad switchgear, you see that most of the live buses are basically insulated. It's more for safety and basically protecting our personnel on that. And also, as you can see, the cladding nature of the external, peripheral. Okay, so next picture is basically the metal clad switch from a different, So basically, this shows you all the front access of this metal clad switch, right? Okay, so from here, remember I made mention that this one is the air core reactor, right? Current limiting reactor, right? Right. Okay, so that is in series with a source to limit the short circuit availability to this side of the switch. The goal is basically to be able to achieve a lower short circuit current and be able to design this medium voltage switch here at the lowest cost. Because if you don't do that, like I made mention, that basically your switch here is going to be very, like 3 or 4 times bigger than this, and basically your bus bars everything is going to be big, and that's cost, right? And space. Space is a premium, then basically you have to incorporate that design. Okay, so this one is a disconnect switch, and this one is the overhead tubular bars, then come in here. Okay, so for the metal enclosed switch here, right, this is the incoming section, right? Incoming breaker. Okay, incoming breaker of the switch here. Okay, and these are the feeder breakers, right? Okay. Then depending on the side, you can have a tie breaker, then another bus. Okay, so this is an example of an incoming section. So this one is the basically the connection point of the incomer before it comes into the incomer cubicle, where basically you have a bus arrangement connections to a breaker, this incomer breaker. Another equipment, very good, very, very important. As you can see over here, but though it's but battery system. Okay, so they call it the DC configuration for a substation, right? Okay, the DC power, right? Okay, so that consists of a DC battery charger and a battery system, right? Okay, so for the battery system, based on my experience, I've seen a 48 volts DC battery substation, and I've seen a 110 volts DC battery substation, then 125 volts DC battery substation, right? Okay, so based on the requirements of your design, and your equipment that requires that voltage, then basically you select the one that you want, and basically the battery design and that needs to be implemented. Okay, so now let's talk about why we need a DC battery, DC voltage, right? Okay, so this is the scheme of basically how the DC battery system works. We have a DC battery charger, right? Okay. Then we have a battery system. This battery system, as you can see here, right? Okay, it's basically in the form of cells, right? Each cell has a voltage, right? So let's say 2.2 volts for each cell, right? Each cell has a 2.2 volts. So it means that I need about 60 of this to achieve 125. 60 or maybe a little bit more than that, a little bit. Okay, so I need a 60 cell batteries to achieve 125 volts DC voltage for my control circuit at my substation. if I choose to select 125 volts DC design. Okay, so some of the equipment that are in the substation, right? Basically, what some of them need DC voltage, and what are these equipment devices, right? Okay, the first one is protective relays, right? Some of the protective relays require only DC voltage, and if it's right DC voltage, whatever DC voltage that you specify. And you have to, once you select that design, you have to coordinate that with the manufacturer of the device. Okay, or maybe work backwards, based on what the manufacturer requires as an input DC voltage for its device. Then, based on that, you select and design your DC voltage requirement for your substation. Right? Okay. Next is your close and trip coil for the breaker. Right, your circuit breaker. They require DC voltage to operate. Okay, so that is what you choose to specify for the breaker. Next is your auxiliary circuit, right? If you have an auxiliary relay, right, ceiling relay, right, that requires a DC voltage, then the source basically comes from here. Next is a lockout relay. Some of this 86 lockout relay requires a DC voltage. And some of the protective relays also require dual voltage, right? DC voltage and either you input in a DC voltage or AC voltage. So you have that option of either utilizing AC voltage also as your so that one has to be a clean voltage probably that can come from a UPS system. Next, protective relay cabinets. Another most important cabinet and equipment in the substation. Right. Okay. So the lineup you're seeing here are protective relays. Right. They are all mounted in each cubicle. Right. And basically, what it does is basically to protect the circuits. Right. Okay. So for a substation, right, we have income lines, right? Transmission lines. Let's say you have a 345 kV transmission line. You have a 230 kV transmission line. You have a 115 kV transmission line. You have a 69 kV transmission line, right? Okay, so then you have a lineup. You can have a whole lineup, in a room, right? Okay. Then one section of the lineup protects your transmission network. Yeah, that is your incomer. Right? Okay, so you see that a lot of these protective relays are, just to give an example, differential protection, right? And they've built a redundancy in you can have a differential protection as the main and the backup, right? It's more of a reliability thing and a resiliency, for the power system network, right? Okay, so you can have an 87L main, 87L backup or secondary, primary or secondary, right? Okay, so that if this one has to be taken out for maintenance or for repairs, then you have a backup. So the difference between that is or if this one fails to operate, during an actual fault, then you have the backup. The difference between the settings are mostly alike. It's just that sometimes they can add a little bit of time delay. Then you can have a distance protection, right? After your primary protection, that is your differential protection, line differential protection. You can have a distance phase, you can have a distance ground, or distance neutral. Then you can have a directional current, right? 67 phase and 67 ground, 67 neutral, right? Directional protection, basically, we incorporate that basically to look in a certain direction. So let's say you have a transmission line coming here, and basically you have a different sources of basically that can produce a ground fault. Then you can set the 67 phase or 67 N to look into this direction to be able to detect ground faults or phase faults as fast as possible, because you have different sources of fault currents that are basically flowing into this section. Next, like I indicated that, you can have a whole lineup of relay cabinets and panels, right? Okay, so this is a typical protector relay, microprocessor relay, right? Yeah, it's, for protector relays, they've evolved for years, right? Okay, they started from electromechanical relays, right? Right, and believe me, there are a whole lot of electromechanical relays that are still in uh, excellent working conditions and basically very reliable. The only problem with that is every now and then they have to be maintained. Like every 5 to 6 years or every three to because they drift a little bit. So during outages, right? During minor and major outages, they are planned so that they are basically removed and basically uh, bench tested, and basically the settings are basically adjusted as per required. Then from electromechanical relays, it basically evolved to solid state protective relays, right? Okay, solid state basically it's just have additional basically elements, right? Basically utilizes power electronics, right? But the now it's a microprocessor relays, right? That has a lot of elements, right? Okay, protective elements that is it's utilizing. In the past, like many decades ago, electromechanical relays, let's say for transformer protection, you can have let's say about 8 electromechanical relays. For generator protection, you can have like 15 electromechanical relays, right? Or if you want to add solid state relays, you can have let's say about 4 or 5 solid state relays. But you, for microprocessor relays, all you need is just a single protective relay that basically has all these elements. So you can see how protective relay relays has evolved in the past, and basically all this microprocessor relay does is it does the work of all this single discrete electromechanical relays does much reliable, and basically offers a lot of enhanced features and that monitoring and really monitoring of parameters, and also the ability to be able to download basically fault records and features data from it in basically real time situation. Okay, so this basically relay lineup shows you on the sub transmission side, right, all the protective relays that protects all the feeders that goes on that sub transmission section of the substation. On this side are test switches, right? Okay, so we have a test switches basically that separates CTs also from the protected relay. If you want to perform current injection, or if you want to perform, we have primary injection and secondary injection. You utilize the test block to be able to do that, right? Okay, remember that CTs has to be shorted, right? You can't leave it open circuit. Okay. Next substation equipment is capacitor bank, right? Okay, very, 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 very important, right? Okay, so capacitor banks basically comes into play. They are reactive power support, right? Right? Q, right? So during the initial design of a substation, right? Low flow, as part of the planning phase of a substation, they perform load flow, they perform short circuit studies, they perform protective relay coordination studies, they perform arc flash studies, right? Okay, so arc flash studies is usually done in that sequence: short circuit studies, protective relay coordination studies, then arc flash studies. And sometimes if you are in an industry that has large motors, right, then they perform motor starting analysis, starting the largest motor with the others running. Okay. Then they do insulation coordination studies. right? And that itself ties into the selection of surge arresters and also the location of lightning arresters on the towers, right, to protect the substation. Okay, so if you do the load flow, right, so that is when the discipline engineer and the architectural engineering consulting company do the simulation, and they find out that after performing the load flow, active power flow and reactive power flow, right, the voltage profiles on the buses, right, violates the criteria, right? It does not meet the criteria. And as for higher voltage, right, it's plus or minus 5%, right? Utilizing the pre-fault voltage of 1.05, right, per unit, right? And at low voltages, right, plus or minus 10%, right? That is what is required. So when they do the load flow and they evaluate the bus profiles, and they found that it does not meet the criteria, right? So that is when, based on the worst case scenario, so that is when they decide that, okay, we need to install capacitor banks to provide their support for reactive power, right? So capacitors are providing reactive power to provide that voltage regulation support to improve the voltage, right, during steady state operation or during fault condition. So that is when capacitor banks comes into play, right? So you can install capacitor banks to be basically energized in stages, right? In banks, bank 1, bank 2, bank 3, right? In stages based on the need, and it can be manually switched on or automatically switched on based on the settings of voltage levels and the amount of reactive power that is required. Okay. So as you can see over here, right, you can see a reactor here, right? Okay, this is an air core reactor, similar to that air core reactor that I showed you, right? Okay, so now the question you want to ask me, what is the purpose of an air core reactor on a capacitor bank? Okay, let me explain to you what a reactor is doing with a capacitor bank. Right? Okay, so if you energize a capacitor bank, right, what happens? There's a huge inrush current full of high frequency transient component, full of high frequency component, which can be very disastrous, can cause power quality problems, can cause problems for other equipment that are in running condition. If you have a motor that is running, right, that voltage dip can cause it to stall because the voltage is not adequate for it to be in steady state running condition. So you utilize the air core reactor, right, to limit the inrush current during energization of the capacitor bank, right, to avoid that transient condition during energization. So that is when you utilize the air core reactor. There are other designs, right, that are in play. One of them is utilizing resistors that are in series, right, basically to limit the amount of inrush current. Right? There are other devices to call it controlled switching, right, that measures basically the sinusoidal wave and finds and determines the actual point on the sinusoidal wave to energize the capacitor bank to mitigate or limit the amount of inrush current that is basically occurs during energization of the capacitor bank. Now, let's talk about disconnect switches. Right? Okay. So, I've made a little bit reference description of it in the previous slide, right? Okay, so now let's talk about disconnect switches in this, as now that you can see it as big as possible, right? Okay, so this disconnect switches, I made mention the purpose of a disconnect switches, right? Okay, so a disconnect switch, basically, it's an isolation device, right? Some people call it isolated switch. After de-energizing, as you can see, right, the disconnect switch is located on both sides, on either, on either side of the circuit breaker. Okay, you have a circuit breaker, right? Right. These are the disconnect switches, right? You can see over here. This is the circuit breaker. Okay. Okay. If I interrupt the circuit, if I de-energize the circuit by opening the circuit breaker, right? If I open the circuit breaker due to, casual operation action or a fault condition, right? Okay. Once I have successfully de-energized this circuit breaker, open it, right? Then I can open this disconnect switches. Either through a motorized action, this disconnect switches actually can be operated by a motorized action, right? Automatically, from remote, or through a manual action. Manually, the operator has to come here and stand on a ground mount and basically manually, operate the disconnect switches and open it basically through the mechanism, the mechanical linkages that basically connect the disconnect switches. Right. They've been designed that there is an amount of capacitive charges and currents that it can break, right? Let's say about 0.5 amps, right? Because as you can see, there's a lot of insulation systems in the substation, right? Okay, so based on that, there's something they call stray capacitance, right? You see this, right? There's something they call stray capacitance that forms basically it's invisible. You don't see, right? Yeah. So the disconnect switches, the no-load operating disconnect switches have been designed in such a that they can break this amount of capacitive charges and resultant capacitive current that occurs due to this stray capacitance to ground. Right. Next, it's a tower structure, right? This is what basically supports the transmission lines coming in and going out, right? Okay, and this one is an example of a current transformer, and I told you how to identify coming in series, right? Okay, so as you can see, two conductors, right? Basically, they've been designed so that they split the current and make it so to avoid heating. Make sure the sizing of the conductors is correct, right? This one is support insulators, right? Support insulators is basically to protect and provide a ground plane to the live conductor. This conductor is live, right? So basically, based on the voltage level, and the support insulators are designed and selected the number of sheds, right, to be selected based on that. Next is a very close picture of the tubular bus, right? How the tubular bus looks like. It's made from aluminum, right? Okay, so this is what carries your current, right? And basically distributes it, in your switchyard. Okay, so one of the questions I'm pretty much sure you want to ask: why this? Right? Okay. Let me show you. Let me explain to you why we have that. Okay, so like I indicated, the civil engineer, right? Once the discipline electrical engineer performs all the short circuit simulation studies based on the worst case scenario, right, and determines the peak asymmetrical short circuit current and provides that information to the civil engineer to design their short circuit tubular bus system, right, to be able to withstand the electrodynamic forces as a resultant of short circuit flow. So the tubular bus is designed in a rigid configuration, very rigid, right? Okay. So based on the environment that the tubular bus is located, right? let's say if you have an extreme high temperature, right? Okay, because it is made from aluminum. What happens? It's going to expand. Not to talk about fluctuation in loading, right? Fluctuation in loading will also make the bars to expand and contract, right? Based on the amount of current that is flowing. So what happens? If you have a single rigid conductor running across the straight length of the substation, what is going to happen? And also, if you have a short circuit condition, it is going to bend and break. So this flexible connection, braided link, they call it a braided link, braided flex link, allows the tubular bars to expand without breaking. And during fault conditions, it doesn't break. Okay, so now let's take a look at this substation equipment. It's a current transformer, right? Okay, so I've explained to you how this one works, right? It's connected in series, so you can see the conductors come. The primary conductor, right? Okay, goes in here. That's here. Single conductor, right? And inside this, you have oil. We have a core, right? Around the core is your secondary winding. Then it comes out, and the secondary winding basically comes to a terminal box, right? For you to utilize either 5 amps or 1 amp, whichever amperage you need for your device, that is metering or protected relays. Okay. So on this side is basically your insulation system, right? Okay, so you have this one, you know, either porcelain or polymer. And some people call it composite, right? Composite. So it's the same, you know, right? So basically, its purpose is basically external insulation, you know, from the elements, right? And also, I explained to you how they are able to achieve this zigzag, right? This zigzag, it's basically to increase prepaid distance for leakage current to prevent flashover due to high contamination in an environment that this substation is located. So with that comes to the end of my presentation, and thank you so much for your listening. Yes, you know, look out for, you know, other more interesting presentations that will come up to you. Now, don't forget to, this is a link to my YouTube, right? Okay, so please go out there and watch all the videos out there, and don't forget to select the like button if you like it, share, and subscribe. Okay, so this is the subscribe, and this is the like button in YouTube, and this is my YouTube channel, right? Please go out there and watch out all the videos out there, right? To basically better, you know, continuously educate yourself, you know, as a practicing engineer, as a disciplined engineer, as a maintenance technician, as an operator, as a young engineer. You know, these videos are very good for you. Thank you so much.